Hello there, Trig students. It's time to move forward into section 6.3 of your book. Remember, chapter 6 is all about just different topics in trigonometry, and so they're a little bit of kind of a mixed match of things. The first two sections were about the law of sines and the law of cosines. Now we're going to talk about another topic that's near and dear to me, because in my previous life with doing science and especially atmospheric science, we did tons of things about vectors, and vectors don't entirely have to do with trig, although there's trig things about them, but they are one of the next important topics that we're going to be doing for a couple of sections. There's a vocabulary word you need to know, and you probably have seen this word before, but it's going to be important here, and that is scalars. Um, Scalars are just a number, a real number. So we aren't talking about any imaginary numbers or whatever. And lots of things that we would measure, maybe most things that we would measure, just take one number, a scalar, to describe them, like temperature. Temperature is 42.3 degrees Fahrenheit, or the mass is 10 kilograms, or the time is 10 seconds after the experiment started, or the pressure is 101,000 pascals, or something like that. But they're just numbers. Scalars are just a number. And 99.9% of what you've done so far in math has been working with scalars. But vectors are for important quantities that can't be described by just a single number. In other words, they can't be described by just a single scalar. The classic examples of things are like motion, for example, where the velocity of an object has both a speed and a direction. And you knew I'd have to throw in the dude from what was that, Despicable Me or whatever, Vector. If you didn't ever see that movie, this bad guy's name is Vector because he has both magnitude and direction, or something like that. Just because I know it would give you a little chuckle here, I thought I'd show you. Where did it go? Where did it go? Oh yeah, Xavier. I had that slide up, and my 10-year-old drew all over it with drawing tools in PowerPoint. It made him scarier and stranger than it really was. And I told him I'd at least show that picture because everybody could use a chuckle. Anyway, where are we at here? All right. So anyway, vector. That's a good way though to remember. Remember the bad guy. He had magnitude and direction. It took two numbers to describe him, not just one. So these are going to be vectors in the plane, and so we're just going to be talking about like motions like in the x, y directions. We'll eventually have three-dimensional vectors in a couple of days. And we're going to start with a different way of thinking about vectors before we get to the main way we're going to be doing about it, because it's kind of easier to picture this at the beginning. So let's say we were talking about some motion here, and we were at some initial point P right here on the plane. Like maybe this is a map or something like that. And then let's just say maybe 1 second later or something, we're at this point Q. That's our initial point P, and our ending point Q. And the right word for what we're drawing here is called a directed line segment. You remember line segments from geometry. We would just call this like the line segment PQ, and then we would have written it PQ with a line over it. Now we're going to make it PQ with an arrow over it to indicate that there's a direction here. We're going from P to Q, not from Q to P. Is this the same thing as rays back in geometry? Well, kind of. Rays went on forever. Vectors that have a magnitude, they have a length, they have how far they go. And in fact, we have a way of writing that number. It's awkward, but it's a double set of bars in front of the term, the name of the vector. Well, with vector, in this case, directed line segment is the right word we're using, although later we'll call this thing a vector. And then a double set of bars afterward. And I know that's a little bit awkward. It has to be a double set of them. Otherwise, a single set of lines around there would be absolute value. And there's no sense to the word absolute value in this case here. So, all right. So this is how we would do the magnitude of it. And in fact, it's not a terribly difficult formula to do. It's actually a variation of the, as well, it's very much the distance formula, if you remember that. So like if point P on this map or with this graph or whatever was at P1 comma P2, and at point Q was over here at Q1 comma Q2, then the length of this directed line segment PQ is the square root of the Q1 minus P1 squared plus the Q1. Oh, I have a mistake. These should be 2's. All right. I did make a mistake here. This should be Q2 minus P2. All right. Sorry about that. I don't have any way to fix that as we're giving this on here. But this definition is in your book as well at the beginning of section 6.3. All right, so I apologize, but yeah, these should be 2's right here. All right, I'll fix that. All right, so we could have multiple directed line segments sitting here on the same graph. And an idea that we will have about these vectors is that they could be equivalent, like they're both really doing the same thing. Like I actually in PowerPoint here just literally copied and pasted this vector down, this directed line segment down over here. And then I called its starting point R and its ending point S. And so I have a second directed line segment RS. But I mean, it's clearly in the same direction and it's clearly the same magnitude. I literally just copied and pasted that vector right there. Well, we want to be able to describe those two vectors or those two directed line segments as being equivalent to each other. They are moving the same amount in the same direction. And the way you would do that is you'd figure out if the problem was asking, are these two equivalent? You first check to see if they have the same magnitude using the formula that we just had before, and then check to see if they have the same slope. Now, the slope, you got to fuss with that. It's going to be the rise over the run. So you're going to check the change in the y coordinate divided by the change in the x coordinate. But you check them both and see. And if they both have the same magnitude and they both have the same slope, then we would describe these two directed line segments as being equivalent. There definitely are problems about this on the homework set. But I know from my notes from the past couple of years that students tend to do very well on this part. And so I don't want to spend a bunch of time because we have harder ideas today than this idea of testing if two line segments are directed line segments are equivalent. But obviously, if you have any questions about it, just write to me or text me or whatever. I'll be glad to explain this in more detail. But like I said, as my experience is that students end up doing well on this. This idea of a directed line segment, we started here and we moved here, is actually not something we do very often in it seems so logical, but that's actually not very often what we do. Rather, more often we move the I wonder if I can move this. All right, so we much more often rather move the directed line segment to an equivalent vector that has its origin at has its initial point at the origin of the graph, like I have done here. I literally in PowerPoint just took this arrow here and I grabbed it and I made a copy of it and put it over here instead. So these two vectors here are equivalent, and the original point of it, the initial point, is at the origin of the coordinate system. And there's actually a nifty term for this. It's called the component form of the vector. We aren't ready yet to learn why that's called component form, but it is it's going to be a whole lot easier to work with this because we don't have both a starting and an ending point. We already know the starting point is going to be at initial position. This works just fine to move the vector over to here, and in many ways makes the math a whole lot simpler. Let's see here. So I have actually right with the Q1s and the Q2s here. That's interesting. So in other words, oh, hey, let's actually write this vector out. So our original vector will have become this new vector, which we're going to write with this. See how these got the angle bracket notation around the outside of it? Angle brackets are the notation your book uses to indicate that these are the coordinates of a vector. If they're just in regular parentheses, the book is saying that those are a point. But if they're in these angle brackets, we're saying that it's a vector. So in this case, we have a vector in component form that ends at the coordinate v1 comma v2, and that is our new vector v. Okay, hey, let's talk about notation for just a second too. I tend to always try to write my vectors with the little vector symbol on top of it. In your book, you're going to notice that sometimes they're just writing the letter V or whatever in bold. Okay, both are acceptable ways of writing something like in a book, but it's awfully hard with handwriting to make it clear that like that V is bold or that PQ is bold. So when you're writing them yourself, write them with a little arrow on top of them. I mean, it's a little hard to do that in PowerPoint or in a Word document or something, but it is, whereas bold is easier at things like that. But for on your paper, please do it with the little vector when you're writing. And the magnitude of this directed line segment, which is going to be the same as the magnitude of this little vector now that we have produced down here that's in component form. Again, once again, I made the mistake here. These are Q2 and P2 here. I had literally just cut and paste this from the other one. I made a mistake. Is equal to the square root of V1 squared plus V2 squared. Well, right off the bat, this looks a whole lot easier to memorize and not make mistakes on than this part does. So, all right, we have a way of determining the length of this vector. And by the way, if that vector's length turns out to be 1, it's a very special kind of vector. We're going to call it a unit vector in the sense that its length is 1 unit long. Much like we can use something that's 1 unit long, like 1 inch long or whatever, to measure things, that's what unit vectors are going to be for too. We're going to be using them to measure things. Vectors, we don't actually use the word really equivalence as much. I know I put that on the slide here. If we're talking about vectors, we're wondering if they are equal to each other. So if I have one vector u, and notice we're going to say that we're going to describe it as having, well, these are its endpoint coordinates, and the way we do that is we write them in angle brackets. So it's at some coordinate u1, u2. We have a second vector v, and it's at, again with the angle brackets here, v1 comma v2. Those two vectors are equal if and only if the first coordinate is equal to this first coordinate of the other vector, and the second coordinate is equal to the second coordinate of the other vector. Basically, they have to be exactly the same. Then the two vectors aren't just really equivalent, they're equal to each other. All right, well, that's kind of just sort of some definition. All right, so we can actually work through an example. This is one of the examples in your book. I'm not sure that this is example 1 or whatever. I didn't write that down. But it says find the component form of a directed line segment PQ. Again, in PowerPoint, it was hard to make that PQ with an overline. If P is equal to, if the, okay, notice I use curly parentheses here, because P is a point. It's at the point of 4, comma, -7, and Q is at the point -1, comma, 5. But there's a directed line segment that connects these two places here. So that directed line segment, which goes from Q1 minus P1, comma, Q2 minus P2, okay, those are its coordinates. And if you do the math, that'll be V1, comma, V2. That'll be our new vector V, which remember we call that component form of the vector. So let's see here. So V is going to be equal to, I just rearranged those. I just literally cut and paste them and rearranged them here. And so you plug in here, it's going to be -1 minus 4, comma, 5 minus the -7. That's plus 7. And you get -5, comma, 12. If I put the vector from this starting point to this ending point, from the point P to the point Q, and then moved it so that the initial point was at the origin, the ending point would be at -5, comma, 12. All right, these kind of problems, there's a handful of these kind of things on the homework set. Once you have the idea, though, these vectors, you can see how they're more than just a number. They're kind of a way of saying numbers, but they're a number that contains two pieces of information. So how far we're going down the x-axis and how far we're going down the y-axis for the ending point of this vector here. There's once you have that, gosh, this is huge in like physics and science and stuff like that, because that could be describing how something's moving, or that could be describing the force acting on something. There's lots of applications of vectors. So once we are having vectors, we can start doing things with them. Like, for example, describing certain vector operations. There are going to be rules that describe what we can and can't do with vectors. And one of the simplest things we can do is just add them. I mean, if I have two vectors, a vector u that's endpoint is at the coordinate u1, comma, u2, and a vector v whose endpoint is at v1, comma, v2, and both of them have their initial point at the origin. That's because they're in component form there. We can add them, and all we do to add the vectors is add the x coordinates and add the y coordinates. And I have a little graph here illustrating what's happening here. So like if I have a vector u and a vector v, effectively what I'm doing here is I'm moving the tail of v to the head of u and then connecting the dots. We're effectively adding them like tail to head like that. And then the endpoint of the new vector is what u plus v will be. So we have like connected the dots effectively on these vectors here. And vector addition is huge. Vector addition like this is how like forces add up. For example, if we've got I'll take an example from atmospheric science. I mean, here's some volume of air and there's different forces on it. Maybe the pressure gradient force is pushing it this way, but gravity is pushing it this way, and maybe the Coriolis force is pushing it this way. And if you add up the vectors, you get the net force acting on the object, which might be nothing. Maybe the forces exactly cancel out, or who knows. All right, one another thing we can do with vectors, their operation, there's actually going to be a lot of operations, we're not learning them all today, is we can do what's called scalar multiplication. We can take a vector, in this case v, is at its initial point is at the origin and its ending point with an angle brackets there is at v1 comma v2. We could always multiply this vector by a scalar, and I'll just use k here for a scalar because that's what your book used. So we could have k times that scalar, that vector, and it would be kv1 comma kv2. You just multiply each of the coordinates in the ending point of the vector by k. So I took a little example of that down here. If v was from here to here, so like that was where our vector was, if we multiplied it by 2, we just literally multiplied its x coordinate twice as much and its y coordinate twice as much, and you just end up with a vector twice as long, but in the same direction as the original. That's scalar multiplication. Vectors are a weird thing. There's actually going to be at least 3 different kinds of multiplication we can do on vectors. This is our first one. It's called scalar multiplication. We're not doing the other ones until future lectures. Your book gives a list of the properties of vector addition and scalar multiplication. I can't. It's on page 423. I forgot I wrote that on there. And the properties of these vectors can all be proven, which we are not going to do. And I do like the fact that it does illustrate here. Look how instead of putting little vector symbols on top of the U's and V's, they went ahead and did it just using the notation of using the vectors are in bold. So let U, V, and W be vectors, and let C, D be scalars. Yeah, they're not in bold when they're scalars. Then the following properties are true. And okay, well, most of them, honestly, if I hadn't told you, you'd probably guess that that's the case. For example, vector U plus vector V equals vector V plus vector U. I think we had that like since like second grade. You may or may not remember that the word is commutative property. The letters can be commuted around. We can change the order. Another rule is that associative property. U plus V, the quantity, plus W is equal to U plus V plus W, the quantity. Again, they can be grouped like that as long as we're talking about just a chain of additions like that. And well, again, you learn that property 1 plus 2 plus 3 was 1 plus 2 plus 3. The same rules worked in second grade just for scalar numbers. Now you're just finding out they work for vectors. This is the additive identity property. If you have a vector U, you add 0 to it, you get the same vector back. Again, you learned that for addition, 10 years ago in your education. This is like U minus U is equal to 0. Okay, again, that's not a huge surprise. If you are multiplying, if you're doing scalar multiplication on your vector in number 5 here, and then you multiply it again, that's the same as just multiplying the numbers originally. So if it was 4 times 5 times U, that would be the same thing as 20 times U. All right, well, that's hardly, again, if I hadn't told you that, you probably would have guessed it and you would have been right, but now I've told you. This is the distributive property. It works just like distribution does for numbers, and you've been doing that since like 4th grade or something. So like if I had C plus D times some vector, or C and D are scalars, that's the same as C times the vector plus D times the vector. Or distributive property works the other way around too. If you had C times the sum of the vectors U and V, that's the same as C times the vector U plus C times the vector V. Again, you know exactly that rule. If you know it so well that you don't even think about it when it's just numbers. If this was 7 plus x plus 7 times x plus y, you would know that was 7x plus 7y. It's just we have to actually write it out. 1 times the vector is just the same thing as the vector in exactly the same way 1 times 7 is 7. What is that called? Multiplicative identity property or something like that. Again, like literally in second grade when you first started learning about multiplication, or third grade or whatever, you learned that, and it was the easy ones on the test. Same with like 0 times a vector is just 0. All right. And this one's a little harder to see. It is the length of this vector C times some other vector is just the magnitude of the absolute value of C times the length of the vector. Again, all of these vector rules, if it weren't actually written out for you and you came across a problem, you'd have probably guessed, just because none of these properties are weird. Later, we're going to see properties of vectors that get a little strange, that like you can't do certain things. But right now, we're kind of just dipping our toe into the idea of vectors. And as a consequence, we're kind of sticking to just the easiest ones. One of the things that we're going to be doing is finding our own unit vectors. Let's say we have some vector v, and it's not necessarily a unit vector. It has some length other than 1, and we want to find a unit vector that's in the same direction as v, but only has a length of 1. This is our little formula here. It's 1 over the length of the original vector, then that'll be a scalar. 1 over a number is just a scalar, times this vector. So it'll be scalar multiplication of that over this vector. And probably the easiest way to do that is with an example. Again, this is an example from your book, but I didn't think to write down like what number this is. It says find the unit vector in the same direction as this vector, the vector that has its ending point at -2, 5. So the starting point of this vector is at 0, 0. The ending point, see the square brackets there, the angle brackets rather there, is at -2, 5. Well, from this formula that we have here, we know the first thing we better do is find the length of this vector. So, all right, the length of our vector v is the square root of the first component squared plus the second component squared. It works out to the square root of 29. Okay, so then 1 over the length of the vector times the vector. 1 over the length of the vector times the vector itself. Here's the vector, -2, 5. And that's -2 over the square root of 29, 5 over the square root of 29. Which again, I mean, is it going to break my heart if you left it that way? No, but I know you'll be more comfortable if your answer matches the answer in the back of the book. And remember, the back of the book is going to be very allergic to having square roots in the denominator of fractions. So we multiplied by a fancy way of saying 1, namely square root of 29 over square root of 29 in this case. So the square root of 29 times square root of 29 became 29, and the numerator became -2 square root of 29 over 29, 5 square root of 29 over 29. All right. This vector right here that we just made, so you can tell it's a vector because it's got angle brackets around it, is a unit vector. It has its length of 1. In fact, in the original problem, it asks you to check that. But how much fun does it look to square this thing and take the sum of them and then take the square root? We won't do that right at this exact moment because it's just arithmetic. But it is in the same direction as that original vector, -2, 5, whatever direction that is. Let's just say this direction. But it only has a length of 1 unit. Unit vectors are pretty slick. There's going to be all kinds of useful things we can do with them. And they can be in any direction you darn well want. However, most of the time we're going to work with a standard set of unit vectors. A unit vector that we're going to call I hat. That little upside down V that's on top of the I here is called hat, which is clever. Anyway, I hat is equal to the vector 1, 0. It's a unit vector just pointing down the x-axis. And j hat, which is 0, 1, which is a unit vector pointing up the y-axis. Those are called the standard basis vectors. I don't think that word is going to come up much in this class, but they are the standard vectors. There's going to be certain standard ways in which we're going to be able to use them versus these kind of unit vectors, which there's certain usefulness to them when they're just sort of pointing in any direction, but they're length of 1. But we're not doing that right now. But notice that this idea of the standard basis vectors, I hat and j hat, gives us yet another way to write the vectors. I mean, if we had the vector 5, 7, well, that's the same thing as the scalar 5 times the vector 1, 0 plus 7 times the vector 0, 1. But 1, 0 is I hat and 0, 1 is j hat. So another way to write 5, 7 is 5i plus 7j. Now, I know that doesn't look better now, but there'll be times in the future where doing it with the i's and the j's will be better than doing it with just the angle brackets and the commas and stuff like that. So we need to get on the path of this with a little bit of faith that I'm telling you the truth. It will be better to do it with these i's and j's in a little bit. So for example, though, just as a problem that would involve the I hats and j hats, let's just say our first vector, we're writing it instead of -3, 8, we're writing it as -3i. Well, let's start that over. -3i hat plus 8j hat. And v equals 2i hat minus j hat. That's asking you to find 2 times u minus 3 times v. By the way, I hat has absolutely nothing to do with I, the imaginary number. Okay, that's not what we're doing here. The I hat is a completely different symbol. Hat is a way in which we write certain unit vectors. All right, anyway. All right, so here we can do, if we're trying to find the answer to 2u minus 3v, it'll be 2 times the way we wrote u minus 3 times the way we wrote v. Now our rules let us know that we can distribute it. That 2 times -3 becomes -6. That 2 times 8 becomes 16. Minus 3 times 2 is 6, and 3 times -1 is -3. Oh, I got a little out of control there with my hat. The hat should just be over the J. And that equals, if you add those up, so let's see, -6i minus 6i is, that should be -12i. Shoot, I made a mistake. Okay, it's -12i. And 16j minus -3j, that should be 19j. All right. So yeah, I have a mistake here. I'll see if I can get that fixed. All right. Okay, so right now I get it that i's and j's look like just another level of complication in all of this, but trust me, with time, they're going to be the best way of describing vectors. But we're maybe not quite there yet. The book decides to spend a little bit of ink too on talking about the direction angle. This is our vector that we're going. It's going off in some direction, a I hat plus b j hat. In other words, the coordinate of this vector here, this ending point here, would be in angle brackets a comma b. We want to find theta here. And honestly, my guess is the main reason they're bringing this up at this time, I mean, we will eventually need it here, is this is making a triangle whose, well, this side is A and this side is B. Well, I guess that opens up the door to us understanding that the tangent of theta is B over A. And then we can take the inverse tangent of both sides and show that that theta is equal to inverse tangent of B over A. Honestly, my guess is the main reason that's in there is they just want to make an explicit connection to trig at this point. It'll come more later. All right, so there's an assignment today. Now, I have put it up on Google Classroom. It's an on paper assignment. I know some people do some things on tablets. If you want to like send me some, like you wrote it on a tablet and then send it to me, that's fine, or whatever. If you do it on paper, my preference would be if you scanned it, but if you don't have a scanner or whatever, that's cool with me. Just take pictures of it. The most important thing with paper on assignments, though, is be neat and have everything very clearly labeled. Clearly label which assignment you're on, what day this is. Make sure there's plenty of white space so I can see what's going on here. All right. Sometimes that when people turn in things that they've taken pictures of, it's kind of a crazy mess. All right, so there's an assignment there, and then there's also an exit ticket that you do that helps me see that you understand what you're doing in a different context. All right, I think that's the end of the presentation. I appreciate your attention in this matter. I hope that everybody is doing well. This assignment is due, let's see here. This assignment will be due according to EVSC's guidance at the end of the day on Friday, April 10th. And that's obviously subject to change if EVSC changes its rules or whatever, but I'm guessing that they're not going to change those deadlines anymore. And I know that sometimes there's been problems where this audio has been dropping out. And if it does, if there's anything that you need explanation, if you need anything explained anyway, just get a hold of me. All right. I'm glad to hear from students, and it helps me know that you're doing the work and that everything will be fine. All right. That's all that we needed for today. And please let me know if you have any questions, and take care of yourself.